They have to listen to me. So go back to the theory of a partial fraction decomposition. Is this abbreviation make sense? Hope this abbreviation makes sense. Somebody shout out the first one. FTA? Algebra, second one. Someone else? Unique factorization property. Someone else? It's not by law. There's something else. What is BI? Bezout's identity, and what is the last one? Long division. Those are the techniques involved in the theory of a partial fraction decomposition. Does that make sense? All right, here's the grand scheme. You're looking at a polynomial f divided by what another polynomial. You see that? That's the whole case. The whole discussion is about one polynomial divided by another polynomial, right? And these are theories about a polynomial. Now I isolated the denominator gx, and what am I doing here? Gx becomes like this. Factorization, right? Factorization. Now, g1 can be linear, g2 can be something, right? Quadratic, but there's no cubic. Remember that part? Yeah, there's no cubic. It's either linear or quadratic. They're all irreducible. What theorem tells you to this happen? Nope. That's a part of it. In general, that's only for odd degree, right? But in general, we don't know the degree. In general, what guarantees that? Fundamental theorem of algebra guarantees that it's like this. We really didn't use unique factorization property anywhere, but it is unique. Only one way to do this, just like number 2015 factored into only unique way. So, doesn't matter how high the degree g of x is, it's going to factor like this, right? Linear or quadratic, whether it's computable or not. Now, that f of g, do you know what this px is? That's a polynomial. It factored out. Why is there a polynomial set outside? If the degree of f is greater than g, then you have to do the long division and set out the quotient right here, px. So this is easy to integrate. So first thing you should do before you factor is a long division and set it out like that. Now after that you have a smaller degree, and then we do, you see the g1 and g2, they don't have a common factor. If they have a common factor, I would put it into single power. Why would I split it like this, right? So I assume all the g1 through gn, they don't have a common factor at all. So you see that I kind of split it into different fractions here. What theorem allows you to do that? If you have a denominator like this, and you can split each of the power into different pods. What theorem in here allows you to split in the first level? That was a Bezout's identity. If you don't have a common factor, they split it like this. The identity guarantees that. What is the last level is that I separated this, each of the one here. So GK, RK, that could be degree 10, not just 2. GK might be degree 1 or 2, but RK could be really large. So at this stage, degree of SK can be fairly large, not just a constant or linear. Then one more theorem allows you to actually go from here to there, where the numerator is all constant or linear, just like the problem we just saw. What theorem is that at the last bit? No, that was a long division. If you divide the long division, you arrive at here. That's one of the advanced problems. So you didn't pay attention to the one of long division advanced problem, you might not understand this one. But SK, we keep divided with the GK, not the GK to the RK, then you arrive at here. So it's theoretically all guaranteed. You arrive at here. Linear divided by quadratic, or constant divided by linear, raise the higher power. Each individual thing, we know how to integrate it. So here, you start with f of g, no matter what the degree of the polynomial is. Fundamental theorem of algebra and Bezout's identity in long division allows you to write that into pieces like this, where individual pieces here is integrable. If I give you ax plus b divided by u squared plus 1 raised to 17th power, with that table in the back of the trigonometric table in the back of the book, you can actually integrate this one, right? So what it says is, in theory, anything you have here, polynomial divided by polynomial, is so-called integrable. In theory, all of them, you'll enter this one, tangent inverse is going to fall out, some log is going to fall out. Do you see that log falling out? 1 over x, right? You may have that, and then some extra polynomial or algebraic part fall out. So in theory, no matter what polynomial you put in here, it's going to be written like this. What do I mean by the last one here? In general, the coefficient that it required to write that down is not computable. Why is it not computable? Fundamental theorem of algebra, the factorization, is only theoretical. We don't know what the coefficient of each of the coefficients. It just exists. You can't really write it down in precise manner. So it's important. Out of all this thing, is one thing that you have to remember theoretically. Any polynomial divided by polynomial is elementary. It's the antiderivative is something that we know, except the coefficients. But if you choose something else other than polynomial here, that there's no guarantee that your antiderivative can be written in terms of functions that we know. But it still exists because of the integrability of a continuous function. Antiderivative always exists. This time we could write it, but for other things we cannot write it down, but it exists in the world of continuous function. Alright, so far this is what we have done. Integration technique, integration by parts, trigonometric integrals, all the powers of cosine n and all that. And the substitution method too. It's a weird substitution, but it allows you to compute it. And then final bit, partial fraction decomposition, which probably you realize that it utilizes both of them all together inside this partial fraction decomposition method. Alright? And these all are used in where? Next follow, of course, differential equation. Chapter 8 is entirely devoted to the differential equation. Everything is very self-contained in differential equation, and the Department of Policies is optional. So I don't teach differential equation here, but you will learn in the differential equation course. They start all from the beginning. But if you're good with this one, you're going to sail through. That's going to be really, really fun course. If you're rusty on this one, that can be pretty painful course. All right. So that's one thing that you need to know about this integration technique. That ends it. So geometry and physics applications, right? And here's an integration techniques. And what's next?